Hi friends, today on 1 Minute Math we're looking at advanced applications of L'Hopital's rule. So I'm thinking of this from like a Calc 2 perspective, assuming a little bit that you've already done a little bit of L'Hopital's rule, and let's see the kind of problem where this might come up. We're evaluating limits is what's really happening here, and this would be a classic L'Hopital problem. I've got the limit as x goes to pi halves of cosine 3x over x minus pi halves, and I notice that if I plug in my pi halves, which should always be the first thing we try, right? When I plug in pi halves for x, I get 0 on the top and 0 on the bottom, and this is very bad. We're familiar with, like, if I get 0 divided by a number, I know that that's going to equal 0. If I get a number divided by 0, that's going to go to positive or negative infinity, or it might not exist if they if they don't agree on positive or negative infinity. But when I get 0 over 0, this is what we call an indeterminate form. Indeterminate. I can't determine it. That's basically what that's saying. It could be anything. So I can't just plug in, I have to do more work. And that's where L'Hopital's rule comes in handy, named after Guillaume de L'Hopital. He's a French guy. There's a great story about how that rule came about and how it got named after him. I'll let you look that up in your own time. So L'Hopital's rule says this: if I have the limit of a quotient and the top and the bottom, like both f of a and g of a, go to 0, then I may say that that limit equals the limit of the ratio of the derivatives. Just take f prime and g prime. This is not the quotient rule, and it's just for evaluating limits, and we're also allowed to apply this rule and take the derivative of the top and bottom if both the top and the bottom go to infinity. So this is the situation we're in. We've got a ratio of 0 over 0, and I'm just going to go ahead and apply L'Hopital's rule, which means I need to take the derivative of the top. The derivative of cosine 3x would be negative 3 sine 3x. The derivative of x minus a number is just 1, and now I can plug in negative 3 sines of 3 pi halves. Sine of 3 pi halves is negative 1, so this limit equals 3. It was a 0 over 0 ratio, but we were able to deduce that it equals 3. That's L'Hopital's rule in a nutshell. But you'll notice, let's go up here to one of these guys, that sometimes we get other indeterminate forms. This is a case of having another indeterminate form. If I try and plug in here, the limit as x goes to pi halves from the left of tangent minus secant. Tangent of pi halves is infinity. Secant of pi halves is infinity, and I get infinity minus infinity. This is another indeterminate form. Do they cancel out? Is there something left over? Is one infinity bigger than the other? I don't know. It turns out that there are tons of indeterminate forms. We've looked at 0 over 0 and infinity over infinity, but infinity minus infinity is another one. And if I list a few more, you'll see a pattern in most of the other ones. 0 times infinity is another popular indeterminate form. 0 times anything should be 0. Infinity times anything should be infinity. So they are in competition. 1 to the infinity is in competition. 1 to any power should be 1, but anything to the infinity power should be infinity. 0 to the 0, because 0 to a number is 0, and a number to the 0 is 1, so that's in competition. 0 to the infinity and infinity to the 0, and you can process those on your own. Those are all our indeterminate forms, and there are not separate L'Hopital's rules for how we handle them. Let's just kind of see how this one plays out. If I'm just using good mathematical skill here, and I know how to simplify tangent minus secant using some trig identities, I can combine these two as a single fraction, and I get the limit as x goes to pi halves of sine x minus 1 over cosine x. Now, sine of pi halves is 1, so sine pi halves minus 1 is 0, and cosine pi halves is 0, and I get myself this nice little succinct 0 over 0 indeterminate form that L'Hopital has showed us what to do with. And now I can just take the derivative of the top, cosine x, then derivative of the bottom, negative sine x, and plug in, and I get 0. Notice how L'Hopital's rule didn't change. I had 0 over 0 as an indeterminate form, and I took the derivative of the top and bottom. That part stays the same. What changes in these advanced applications, like how do we deal with these other crazy indeterminate forms? What changes is that we're going to be clever in trying to come up with a fraction that will give us a 0 over 0 or infinity over infinity indeterminate form, so we can use L'Hopital's rule as we know it. Let's take this guy. This is a great one. If I plug in 0 there, I get 0. The natural log, the limit as x goes to 0 from the right of natural log x is negative infinity. So I've got a 0 times negative infinity thing happening here. That's an indeterminate form. So my strategy here, and we could process this in great detail, but I'm just going to give it to you. I'm going to consider a new variable. I'm going to call it h. And let's let h be 1 over x. Now, if x goes to 0 from the right, h is going to go to positive infinity, and I can rewrite this limit. The limit as x goes to 0 from the right will be the limit as h goes to positive infinity of 1 over h times the natural log of 1 over h. And fancy, I can write this as a fraction. Woohoo! Now I'm going to get infinity over infinity again, and I'm even going to use a log law here real quick, noticing that 1 over h is like h to the negative 1, and the natural log of h to the negative 1 would be negative natural log of h. This limit could be written as the limit as h goes to infinity of negative natural log h over h. And this is very clearly a L'Hopital situation. That goes to positive infinity, that goes to, or negative infinity rather. This one goes to positive infinity, and I get the limit as h goes to infinity of negative 1 over h over 1, which gives me 0. Sweet, right? I'm going to succinctly collect all of these for you right down here in all of our indeterminate forms. Here are our strategies so far. If we have 0 over 0 or infinity, take the derivative of the top and bottom. In an infinity minus infinity situation, we find a common denominator or somehow try and combine our fractions. And if we have a 0 times infinity situation, we're going to use a substitution of x or use whatever variable you like. I actually often will use a w because my h's look a lot like when I write natural log. But h is kind of like the standard variable we use. Make substitution that will allow you to get a fraction. And remembering here that our whole overarching strategy is to make a 0 over 0 or infinity or over infinity fraction. I will point out that sometimes it doesn't end up being 0 over 0. And sometimes we get a fraction that is more easily evaluatable, and that's even better. Our last one are these guys. In this case, if I plug in 0, I'm going to get sine of 0 is 0. 1 over 0 goes to positive infinity. Let's make this go to 0 from the right. And I've got a 0 to the infinity situation. Our strategy for these, we need to get that power out of an exponent situation. So I'm going to not write an equal sign here, but I'm simply going to consider what happens if I take the limit of the natural log of the expression that I'm given. Now I can apply a log law, a property of logarithms, to pull that 1 over x down. 1 over x, now I can make this a fraction just using some algebra. Natural log of sine x over x. Sine of 0 is 0, that goes to infinity. 0 goes to 0. Infinity over 0 actually is infinity. This is going to be a negative infinity. So my answer here will be e to the negative infinity, which is 0. All right, the answer that you get for the limit after you put the natural log on, that's not your final answer. Your final answer will be e to that power, because you're basically saying you're taking the limit as x goes to whatever of e to the natural log of the original expression that you were given. Making that e and log cancel out, that would be a way to write the limit as x goes to a of f of x. So again, in succinct form, here's this little chart. This last part, take the natural log of the argument, and then as a reminder, don't forget to do e at the end. Don't forget e to your answer. Yay. All right, that's how you deal with advanced applications of L'Hopital's rule. I hope you learned something. Thanks for watching.